Alright, so today we're going to talk about auto associators, and then the homework will be to do some basic training problems using Friday's scripts. So on Friday's folders, there's one for Python and one for MATLAB. And those are basically self-contained. The MATLAB one is self-contained. The Python one brings in a few built-in functions that are standard. Okay, so there'll be a homework sheet for that. Basically, I want you to just go through those files and either Python or MATLAB and modify them in order to do some regression problems. All right, so what I want to talk about though today is the Autoassociator. And it's a special type of neural net. Oops. So the idea behind an autoassociator is you have an input layer, and then you have a middle layer, and then you have an output layer, kind of just like a normal neural net. And then this would be fully, typically, I'm drawing the basic case here. You know, you could modify it or customize it. Okay, and then you have an output layer over here. And so this is, I'm thinking of this as being like fully connected. That's not a very good picture. Let me pause for a second and draw better. Okay, so here's a little bit better. In this case, I'm going from R5 to the hidden layer in R3 and back out to R5. And now the important thing about an autoassociator is that the input dimension is the same as the output dimension. Now the middle dimension, it depends on kind of what you're doing, but typically this is of lower dimension than the input and output. Okay, and so the idea behind an autoassociator is you have your data coming in, and then it's being mapped to a low dimensional space, but then it's being mapped back out. And in this case, what we want is we want the output equal to the input. In other words, what we're trying to do in the autoassociator is we're trying to build the identity map. Okay, and so what makes the problem non-trivial is that you're trying to do, or you're typically trying to do, a compression right there. And so you're trying to compress the information to a lower dimensional space and then uncompress it on the other side. Okay, and so typically we don't just go in reverse for these two steps. So this would be like a W1 and a W2, and these weights are independent of each other. We also, on the hidden layer, we typically would allow a nonlinear activation function. Okay. You might be asking why we would do this. Well, the idea is that once you're finished training this network, then you can break the autoassociator apart. And so the two pieces then would be the first one, right, so that the output layer is actually the middle layer, the hidden layer is now the output. And this network is called the encoding network. Oops. Then of course you can probably guess the other one. This would be the hidden layer, and this is now the input, and then this would be the output, the original output layer. And so this is the decoding network. Good. So the encoding network would go from your high dimensional space, usually Rn, to your lower dimensional space, Rk, and then the decoding would try to go in reverse, Rk to Rn. Okay. So what would one of the uses of the neural network be? Well, you might recognize this dimensionality reduction problem as something we've already talked about. And in fact, if you were to leave the activation function as a linear function, what would be the best three-dimensional hidden layer that you would be able to get out of a Autoassociator? So if we had a linear transfer function, or linear activation function. I keep using the word transfer function because I'm old school. People are calling it activation now. Activation function. Then we proved that the best three-dimensional representation of the data is performed by principal components analysis, or PCA. Okay, and so what we're trying to do by doing this activation function that's not linear, we're hoping to get a better representation in the lower dimensional space by allowing this nonlinearity to occur. Okay, but we're still going from, like presumably a high dimensional space into a low dimensional space, and so typically you would assume that there would be some loss of information in this, going from R5 to R3. And so just to let you know, R3 to R5, this mapping is sometimes the hardest part to get, because once you've lost that information in your projection, you're not going to get it back, right? And so, yeah, so sometimes that can be kind of tricky to work with. But that's a good thing to think about. By the way, I should say, modifications include, oops, things keep popping up here. You don't just have to have one hidden layer. You could have an input layer followed by a big layer followed by a small layer, for example, and then you would repeat or go in reverse of that. And it's usual to make this mapping symmetric, although it's not really required. Really, the only thing that's required, right, is that you have this encoding followed by a decoding. And so as long as you can get from your large dimensional space, from your Rn to your Rk back to your Rn, whatever layers you have in the middle are pretty much irrelevant. It just depends on what how much how many you might need in order to represent the information that you want to represent. I will say that it's kind of interesting. Sometimes it is better to map to a high dimensional space before you go to a low dimensional space, because if you map to a high enough dimensional space, data tends to become uh, linear, uh, separated from each other. And so if your data is kind of mixed together, by mapping it to a high enough dimensional space, you may be able to unmix it before you bring it back down into R3. Okay, so that's just kind of what may happen. Now, we don't have a Autoassociator built in from scratch, although MATLAB, you can build it from MATLAB and you can build it on Keras, which is the something we'll talk about later. Um, so I might run a video that shows the training in MATLAB so you can just see it, because really it's why am I bringing it up at this point? Well, there's a couple reasons. The biggest reason is when we talk about deep learning or something, a lot of times what they're going to say is, well, you want to pre-train your network before you actually bring the inputs and outputs together. And so how would you pre-train a network? So suppose I've got this network that I want to go from like R5, and then I have like 10 nodes in the hidden layer, followed by a three-dimensional net. Well, the idea behind the pre-training is that I would just go ahead and attach another 10.5 network here, and then I would train the Autoassociator to try to build, to try to go from your domain to your domain. And so this is going to build without even looking at the output data, right? Your desired output data. And so this is really just trying to encode your domain in such a way that it's invertible. And so this is a useful technique because it's really focusing on trying to figure out how to encode your domain into these nodes, right? And so we're going to have to, at the end, right, you would then split up the network, and then you would just focus on your encoding phase, or encoder, and then you would train the encoder. Now I should say for smaller networks, this you don't have to do this. Train this on your data. This is really what you would do for a deep network, and yeah, I think I'll save that for the discussion on deep networks. Okay, and then what we'll do for the next video is just take a look at how MATLAB would perform this, and also we'll take a look at a Python Autoassociator as well. All right, I'll see you there.